Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to welcome Damien Zoufre again to Microsoft Research. Some of you might remember him as an intern about a year ago when he started the P project at MSR. And he's visiting us again. He'll be here today and tomorrow. He just finished his PhD from Tom Hensinger's group at IST Austria, and he's starting a postdoc in Martin Renard's group in the fall at MIT. And he has a variety of interests in formal methods, in language design, reliable systems. And today he's going to tell us about some work he did automating separation logic using automated theorem proving.
Thank you for the introduction. It's always a pleasure to be here visiting MSR. So this is a joint work with Rizca Piskac, which is actually visiting MSR those days, so she's around for the week, and Thomas Wies at NYU. Okay, so what's the motivation? Is that okay? Separation logic is pretty nice to express succinctly very complex invariant over heap data structures, and it has a lot of good features. For instance, separate special conjunctions allow you to easily reason about aliasing and which elements are in some subpart of the heap and which elements are in the other subpart of the heap, and to make sure that those are different. There are also inductive predicates like lists, trees, which allow you to easily define data structures or shape of the heap. And then there is also the frame rule. So the frame rule is extension of all logic for separation logic to also reason about basically frames, so that when you call a method, only the part which is touched by the method in the heap will be changed and the rest is not changed. Now, what is not that nice on the other hand is that, well, even for decidable fragment, in general, separation logic tends to use specialized prover, which means they are hard to integrate into some much larger framework. And it's also not clear within those fragments how you combine them with different theories. So if you want to do reasoning with integers because you have pointer arithmetic, then we like to bring all down to some, basically what we'll try to do is reduce some decidable fragment of separation logic down to some first order theories and preserve decidability. Okay, so maybe just the example of a very simple concat method takes two lists and returns a single list. So the first part will be the specification. So, so we have like pre and post condition and invariant. So we assume that all our programs are notated. We don't do any invariant generation, but just we'll see how to go from this part and those parts, which are expressed in separation logic, actually in the fragment of singly linked list, down to a first order boogie-like program. Okay. So that was then also what that was for the specification. Okay, now what does this thing mean? That so here we have these inductive predicates, which define lists as a sequence of node, and here starting from node A going to null, so from A to null, and here the same for B to null, and here in the middle we have the star, so the separating conjunctions. So concretely, that means that the whole heap can be so the part of the heap which is touched by this method can be divided into two parts, which are disjoint, and one containing one list, the other containing the other list. Okay, and here in the definition of list segment, the last node, like here null, is not part of the allocated heap. And again, here for the invariant, so we have two list segments, and the separating conjunctions, saying that those two are disjoint. And what we can see is here the list segment does not include as part of the footprint the last node. So here cur is not considered as part of this list, but cur is part of the second list. Okay, And then now about the frame inference. So when you start executing the program, you get to the loop, and you want to the loop as a as an invariant. We need to check that as precondition, which basically says that this loop will modify two list segments, one going from A to cur, and the other going from cur to null. So we look what we have in our heap. So okay, we have a list segment from A to null, which is good. But then we have also this list segment from B to null, so which is not going to be touched by the loop. So here basically we have the require as a precondition, and then we have the invariant that we want to prove, but this is not the whole heap, so we here need to find out the frame. So basically figure out that this part is actually the frame. Okay, so that was the nice features of separation logic. And what are our contribution? Well, we reduce while preserving equisatisfiability from separation logic, so the fragment of single linked list, to decidable first order theory, so that then we can fit into the SMT solver framework. Then we can do satisfiability, entailment, frame inference, and abduction, all using automated provers. I mean first order provers, and then we can will also be able to fit this decidable first order theory that I will show later into the Nelson Open framework and combine it with other theory. And finally, at the end, I will speak a little bit of the implementation in the Grasshopper tool. Okay. So first we'll just go over the translation and then second part the implementation. So first, what are which is this decidable fragment of first order logic we are looking? So it was introduced by George Bird and his collaborator in 2004. So it's separation logic formula for singly linked list. So basically, formula can be equality and disequality of variables. Points to mean that the cell on the heap X point to the cell Y. List segment, I will show later what they are defined, and also the separating conjunctions of two heap. And so that was the original fragment, and here we'll extend that with some Boolean structures on top of that. So on top of this separation logic formula, you can apply negation and conjunctions.
How do you interpret sigma? When you interpret sigma, do you imagine that there is a variable called heap?
Yeah, I guess that will come here. So you mean when you interpret this? So yeah, that's now the semantics. So how do we interpret this? So we have something which is equivalent to the standard definition, but slightly different. So in the sense that we have both some interpretation of the heap, which we'll consider as total, so for every variables, and then a subset of the heap, which define over which subpart of the heap the formula that should apply. So we call that the footprint.
So A is a map?
Yes, exactly. So it's a it's map. It's a bit more general because so here for the moment we'll have consider just one pointer, which called H. So here A will be the map, so giving the interpretation to H. So giving taking cell node as argument and returning the nodes that is pointed by this. So yes, in that case, it's a total. It will be a total map.
From int to int?
Nodes, what we call nodes, so memory cell to memory cell. So we just, for the moment, keep the type disjoint. We'll need to combine that with array theory if you want to merge integer, and I will speak about this later. Okay, yeah. So here basically what it says that when you are speaking about equality and disequality, so interpreted in A, so the semantics just check whether this is true or not, and the footprint of those two formula is empty. So here we use the typed interpretation of separation logic formula. So you assume that a formula H is defining precisely a subpart of the heap. So you cannot have anything on the side. So everything must be touched.
I still don't understand what. Okay, what is X superscript A?
Oh, that's the interpretation of X in A. So with the value that A is giving to X.
A is
So A is giving interpretation both to variables and to the function H. So in the sense, H is a map, and for the variables, it's just giving them a value.
Subset X is a subset of the domain of A or the range of A?
It would be actually it will be both because in some sense the interpretation of the heap is total, and here it will be actually it's the union of the two, so it's over subset over the whole heap. So it's just saying which part of the heap you are touching. So you can touch part of the range and part of the domain of H. Yes.
So the normal A's there should be curly A's.
Yeah, the one that's two A's.
Bullets 2 and 3.
Oh.
There is no distinction.
So here, yeah, okay. So sorry, that's the one.
They're all curly A's.
They're all curly.
Yeah, they're all curly.
Okay.
Yeah, perfect. And okay, so then the point to, you start looking into the interpretation to find the value of the map, which, so given here we'll call it H, and the footprint will be just the node X, so as in the classical separation logic. Then for separating conjunction, question?
Yes, so for this heap, the mapping is from the current to the next node? Is that what?
Yes, so here the current to the next node. So here we'll denote that by function H, but then later we can have multiple pointers if you have structures. But yeah, it's just the pointer to the next node.
So for any last element in the linked list, that would be null? Or because I didn't
not necessarily. I will see on the next slide how the list is defined.
Okay.
At least list segment, so you give both the start of the list and the last node of the list.
What is that? What is this?
Oh, that you substitute. So here, when we evaluate H1 in the interpretation, actually X. Sorry, typo. So actually here, instead of X, you put U1. Yeah. Actually, that was copied from. Yeah. So basically, it's forget it here. Just think of that. So when you evaluate the subpart of the heap of the formula H1, you just instead of X use U1. So it's just for the footprint. Yeah, that was a typo. So basically, when you evaluate the two subparts, first you have this existential quantification of guessing the separation somehow, and then you evaluate. There have to be disjoint, and yeah, actually here we can also have interpretation of X in A. So yeah, I should clean that up. Basically, you guess two subparts of the heap, which has to cover the whole heap, so the whole X, and that have to be empty. So disjoint, the intersection is empty. And then when you evaluate the subpart, you will just, instead of X, use U1 and U2. Okay. Yeah, that was a mistake. Sorry. Oh, okay. Then for the list. So for the list, basically we consider only finite lists, so no infinite list. So basically a list segment going from X to Y. So correspond to this. First you guess the length of the list, and then you say, okay, a list of length 0 is just say that the two nodes are the same, and the footprint of an empty list is empty. And then there is this inductive definition that says that that going from X to Y, there exists a node. So there is a node U, such that okay, I'm very sorry. So basically, you say that the list. So you have X point to Z. So Z is the successor of X. And so you introduce this new variable Z, which has value U, which is a node. So in the interpretation, you pick one node, and then you say you have X point to Z. And then you have a list of lengths n, so just one less. And basically you have this inductive step, and then you need to force inequality of variables. That's given by the separating conjunctions. And then the interpretation of the Boolean connective, just that the conjunctions basically is taking the conjunctions. And here, what is the difference between this? That here there is no separation, so there is no need for guessing two parts of the heap over which to interpret. They are both interpreted over the same part of the heap. And for the negation, basically, here we just leave the negation from the as not the interpretation of the formula.
What's the role of z in the third line?
I think z is supposed to so it's just okay. I think there was a mismatch between variables and the interpretation of variables. So well.
Where is it bound?
Yeah, I think actually. Okay, basically z should be bound, yeah, with u.
So you quantify over a variable.
Yeah, so well, here we have we know that there exists a successor which is different, and this successor has to be a node. So in the interpretation, but yeah, it should be bound also here. Yeah, so you guess a variable in the heap. You guess a variable in the heap, so it should be quantified. Then you give it a value in the interpretation. And then you just say that z should be the successor of x.
So it's basically the intermediate.
Yeah, exactly. That's the one-step successor.
Right, which is going to be existentially quantified away.
Yeah, it should be bound
Right,
here.
Yes.
Yeah.
And u is also, but where does...
U is just to give an interpretation of x, of z. Sorry. So you just say that it's in the
there's some
interpretation.
edge, yeah.
So it's just to give to say that it's there
So
in the
essentially you're
interpretation.
saying there exists an edge such that x goes to z goes to some other u. Right. Okay.
Yeah. So there is an edge to the next successor, which has interpretation and then recursion. So there is
Do
a
you want to say that u is in that ls of n?
no
y? Or is that just understood?
No, it's just to say that we wanted to say that some more actually here instead of u we could have like z of a, so the interpretation of z in the
Yes.
so it's just that the role of u is just to give a meaning of z.
Okay.
So I think when you write there that the a with the z goes to u, I think it seems to me that you're not intending a substitution. You're trying to say that z is the thing that already maps to u. Something. Because you don't want to change the...
That's not a substitution, that's an edge roosting. Right? That's z is...
So you just want to grab to say that in this interpretation
it is
you just
already
take
the
those-
case that there's such an edge, right? I mean, you
Yeah.
just say A of
Yes,
z
it's
is
just
equal to
giving.
u.
It's just saying that So there was so by the property of the interpretation being total, you know that there is a u being mapped to the successor, and just you want to name it z. So it's just,
Oh, it is a substitution. Oh, I'm confused now.
so yeah, the idea is that the interpretation A is total over the whole heap, so the function successor is defined. So you just want to someone name that successor z. So you will just in the interpretation give a name to the successor.
Why is x not equal to y at kind of the meta level, but z not equal to x at the formula level?
Okay, here I think there is also some. Yeah, I think. Yeah, actually here that should be. Yeah, that's missing. Sorry, because it is somewhat implied by the separating. Actually, it's implied by the separating conjunction. But let me think if there is some detail.
Not if n is 0.
Yeah. Oh. But basically here, if n. Okay, I should add n strictly greater than, because then, yeah, sorry.
When you choose z,
Yeah.
you're choosing a z that's not in the domain of A. Is that correct?
Actually, so yeah, we want to introduce a fresh name to be sure there is no clash of name.
Okay.
So in that sense, yes, Z is fresh, but it corresponds to an element which is this U, which is already existing in A.
Okay.
So it's just introducing a fresh name to avoid clash.
So you don't say Z superscript A because you can't look up Z and A instead.
Yeah.
Is that right?
Well, we know that Z at that point Z superscript A is U. But yeah, I think that's pretty okay. That should be the way of doing it would be to. That's related to this question of quantifying Z and saying Z is not the same, so you get a fresh Z. Okay, yeah. Oops. Okay, now about the graph reachability part. So here we have a few terms. So terms can be nodes in the of type node or apply h, so this successor function. Then we can have equality over terms. Then the reachability predicate. We'll explain later the reachability predicate. And stratified set. So what will be so that's some first order logic fragment that this part has been introduced. Well, this part is fairly oops, sorry. So I think so there. So okay, maybe I should just explain that more clearly. So the idea is that we'll lift our separation logic formula into this two parts. So the part that was A will become related to this graph reachability part. So it will be giving interpretation to the successor functions, to terms, to node in the heap. And then since we will not be able to have this total interpretation over every node, we'll somehow have partial interpretation of the heap and use this reachability predicate to substitute for all the nodes that are there in between. For instance, you have a list segment, you don't want to check for so you want to abstract for every single node in the list. That will be the total interpretation. And just say you following the pointers along the list from one term to the other. So that's the reachability predicate.
What is H?
H, that's the successor function. Because, so basically...
Is there just a single H or there could be lots of H's?
For the moment, we'll have just a single one. At the end, I will talk about extensions that you can have multiple ones. But here the idea is H, what is this term? So here it says that you can, from this term to this term, so you can reach this term to this term without, maybe I should go to the next slide for the semantic. Okay. Sorry. So it says that you can reach this term without seeing that term in the past. So that says you can reach this from this you can reach this, and you won't see that term along the path.
Just like with right now, so put under the arrow.
Yeah.
Oh, okay.
Yes.
But then we have, and for the set we have stratified set, so classical set operation, also set comprehension. Then here in the set comprehension we have some syntactic restriction that will be needed for decidability. That you cannot have the term which is bound in the comprehension occurring below this successor function into the definition of the set. And then we can have set equality and testing for test membership. And then on top of that, we have kind of arbitrary Boolean combination of those two parts. Okay. Yeah. So maybe just, yeah, so those parts about this theory of graph functional graph reachability, just types of the element in here at node. Here we consider just one successor function, which is h, but you can have a finite number of, a fixed number of h if you want to, so for the theory. And then we have predicate symbols like here, that's ternary reachability. So going from A to B without seeing C. And okay, stratified set here will have as element nodes and set, and function symbols, well, empty set, which is arity 0, and intersection union difference, and as predicate membership. Okay. Okay, so maybe I should have put that slide before. So why we're speaking about function graph in this reachability? Because we assume that this function, this successor is really a function. So from any node is mapped to another single node. And why do we want this to be functions? And why graph that not just functions? Because the interpretation is really function that you can follow. And but here we want to take and reason about transitive closure, so about this reachability predicate. So we are interested in paths and not just the direct successor. And here, okay. So here, this means that from term T1 to term T, you can reach term T2 following a path along the function h without seeing term T3. And we'll use also this list as a shortcut for, so we'll use sometimes the binary reachability as shortcut from saying that you don't see the last element, because, well, in the definition, we'll see the axiom later, going from x to x without seeing x is true, because you don't need to follow a path, we are directly in the node. And also we use another shortcut, which is between x and y. So it's defining a set of all the elements between all the z between that can be reached from x following h without seeing y, so all the node in betweens, and especially excluding the last one. So, okay, what does that mean? Maybe. So we have, let's say that you have three nodes, x, y, and z. And here you don't want to have like, you want to reason about the path. So when I'm making this dashed node, that means that can be many nodes in between in the heap. So here you have a path from x to y, and a path from y to z, and z might be, for instance, null, so it's pointing back to itself. And we have three graphs. Then here you have a path from x to y, and then y has some other path, but it never goes to z. And here x, y, and z, and these may be looping back to somewhere between x and y. So now we just check the values of these predicates. So for instance, going from x to y without seeing z is true in all of them, because there is always this segment. Now going from x to y without seeing z is false in all of them, because going from x to z, you always need to go through y, because there is single successor, so you cannot have other path. Then going from y to z without seeing x is true in the first two, and here it's not true because there is no path. Here again there is no path. And what's the next part? Oh, here that you can have path pointing back to somewhere in between, so you don't necessarily need to know which node it's pointing to have paths going here. So those paths can merge somewhere without knowing exactly the position of the merge. And then in the end, z to x. Okay. Again, there is no path from z to x. Okay. So the usual way, actually, that has been done a few times is to say that we translate separation logic from to first order using two different parts. The first part is to translate the structures of the heap. So that was in our semantic the definition of the interpretation of the value in terms of so of the variable in terms of cells in the heap, and the interpretation of the successor function. And then to have sets to encode the footprint of the formula. So, but here we'll do something slightly different, because, for instance, we want to have a uniform way of dealing with entailment check. We need that we need negation on top of the separation logic formula. So if we just use that transformation, we will lose decidability.
I got a question. If you didn't have the list business inside your separation logic fragment, right? Is it still a challenge? Or I'm trying to understand,
yes.
is it a challenge because of star, or is it a challenge because of lists?
Here it will become because of the star. So the list will map fairly directly to this theory of graphs, but then the star it will be linked mostly to the footprint. So we see that at some point you have this existential over the two subpart of the heap. So when you take negation, they should become universal.
Okay.
And that's really bad.
Why is that bad? That's first order logic.
Yeah, but we want to preserve decidability. So you have this theory of lists, or I mean, if you even remove, which is decidable. So if you remove list, you're also decidable, and you want to preserve that decidability. So you are mapping to these sets as first order set, which are existentially quantified. As long as you are existentially quantified, you are easily decidable. And then when you take the negation for like entailment check, those existential will flip to universal one, and here you might lose decidability. At least I think in the case of list. Yeah, if you have this direct translation, you lose decidability here. Otherwise, we have slightly more complex transition to preserve decidability.
Would it be fair to say that if I did not care about efficiency and decidability and whatnot, if the only goal was to convert to first order logic, this is trivial?
Yeah, because you just take the semantic definition and in line. But here the problem is that when you have this separating conjunction, we need to guess the subpart of the heap, and when you take the negation, we say that for all possible partition of the heap, this doesn't work. And I mean, the critical part will be this for all partition of the heap. That will be introduced by negation. So actually, we have a slightly different translation that says that actually this part, which is general the structures, so it still has the interpretation of the node and the successor function, but it also has some information about how the different subparts of the heap are connected. So which part are disjoint, which part are the union of, on which part are empty. And then here, instead of all the constraints about the footprint, we just keep the definition. So what will be, we'll see what are the definitions. So that's just the leaf term in the translation. So the translation, which should come here, will go basically recursively over the formula and generate these two parts, one part above definition of this set. So here we have the question is, translation means the structures of x equal y over the footprint set big Y. So here it says that, well, we have equality, and definition of y here, there should be the empty set. For not equal, again, the same. Now for the translation of x point to y, okay, we say that the successor is y, but we say then the definition of the part of the heap over this formula is interpreted is x. Now for the list segment from x to y, so basically we have this map directly to this graph from x to y, and here we have this the set of the part of the heap, the footprint of this formula is basically all the node between x and y, so including x excluding y. And now comes really the tricky part. So one of the first tricky part is to say that, okay, we will recurse over the two subformula. And for that, we introduce two fresh sets that will be then defined into the translation, into G1, G2. So, and then we'll just put this as part of the definition of the set. Then we have introduced this fresh set, but we still need to define this y. So the definition of y will come here. So the union of the two subheap. And then on the other hand, the question of disjointness will be put on the part about the structures. So the structures of the two subformula are here. And then we have also to say that those two subheap are disjoint. So here that's one of the critical parts is to separate the definition of y from the constraints over y. So that was for the part of the separation logic formula. Now for the Boolean structures on top of that. So okay, so you have conjunction negation, and when you get to the end of the Boolean structures, you have the heap, separation logic formula. Here we allocate a fresh variables and call the structural translation we saw in the previous slide. And here we need to push to again define x. So x will be defined as equal to y. But again, we need to keep, so y is defined here, and this we don't need to touch. Because now the part is the negation. So what does negation mean? Well, we just have this recursive translation, and here we only negate the constraints over the structures. We do not touch the definition of the set. And that's the second critical part. Okay, then for the conjunctions, it's just intersection of the structure and the definition. And for the top level, just take the union of both. But here we have these two critical parties. Here the negation is not applied over the whole formula. And previously we saw that here we somehow split the y into the definition and the constraints over the set.
Damien, just to check my understanding, the constraints on H means you can't represent a tree that knows its children, right? Can you represent let's say a binary tree where the node knows its two children? But that's, I guess, not.
So not in this fragment.
The parent, but not.
Yeah, this fragment you can do the. That's some extension we want, because here basically you see that the thing we need to reason about this segment is something in the first order theory that directly match and that is decidable. So as extension we could extend that to a decision procedure. So first order theory to reason over tree, and then we would be able to here have like tree predicate. But that's not something that we have implemented yet. But then if you have this, you can use exactly the same idea and generalize the translation to get, because somehow, the trick that you need to prove decidability are in the separating conjunction and in the negation. So they are not in the definition of those predicates. So you really just need to find a theory that somehow match a decidable first order theory that match the predicates, the first order, the separation logic predicate that you want to reason about. So. So example the translation. So we have this acyclic list, which is non-empty. So from x to y and y to z, and then we have this additional constraint that z is not equal to y, to x. Sorry. And then how does that translate? So well, the first part is this. So here we have the two parts: the structures, the definition of the set. Then for the pointers, kind of the same, so just the successor in the part of the heap. This segment, this reachability predicate, and the between. And now, okay, the intersecting part are for the separating conjunctions, we have one part which is the structural constraints that say that those two parts are disjoint, and the other part is saying that y1 is the union of the two. For the other separating conjunctions is the same. And then at the top level, we have the definition of x equal y1. So now it becomes interesting is that when we have negation on top of that. So here that's exactly the same that we had as before. So I'm just ignoring the negation now. And now, so that's just this inner part. And I'm going to apply the negation. So this part did not change at all. But this part, on the other hand, you just apply negation, as you would expect. And here that's the negation normal form. And the question is now, why do we need to do that? So here in G, we are introducing this variable y. And they are existentially quantified. And we need to keep them existentially quantified. And the problem is that, if we had negation, they might flip to universal. So what's the observation that allows us to do this interesting, to apply only negation on the F part? Well, we see that this y1, before they are defined only as set comprehension or a union. So which means that in any given interpretation of the heap, you can find, so the part G will always be satisfiable. And actually stronger than that, what we can prove is that due to this tight semantic, that the formula that we have written over, interpreted over whole heap, actually there is exactly one single assignment to this y variable that makes the definition true. And now what is interesting is that if this existential quantifier has a unique solution, well, we can flip from existential to universal while preserving equivalence. So here, basically, those two formula is equivalent because for all solution or exist a solution, if we know that when there is a solution, there is a single one, it's the same. And here, what happened at the negation actually is that we'll apply the negation just on that term and flip the universal to somehow stay in this nice case and just have negation over f. So that's actually the core of the translation and proving completeness and decidability is that observation that really need to somehow split the definition and make sure that those subsets are unique, those subparts of the heap are unique. And then when we take negation, we can just preserve the quantification as existential. Okay, so now maybe just quickly now that we have this translation, what do we do with those formula? So this formula over this graph reachability and stratified set has two parts, the part about sets and the part about graph reachability. So we'll just speak quickly about the part about sets. So what happened with the sets? Okay, you just put everything into normal form. For every set which are not equal, you can replace them by fresh variable that is in the difference, in the symmetric difference. Then we can eliminate set comprehension. So each time in some context that you have a set comprehension, you just introduce a fresh set variable, and this you add a some axiom, so universal clause that says that you define the membership in the set X as the value of the predicate R. And then we need to eliminate those universals. So that's now why we need stratified set. And what is nice about this theory is that this is a local theory. So what does that mean? That we just go over the formula and collect all ground terms of sort nodes. So all the terms that do not contain any quantified variables. And then we just expand. So for every ground term, we generate a conjunction of the clause. And then basically we have a quantifier-free formula in the end. And since the theory of stratified set is local, this instantiation is complete. Then the part about, so that's the part about set. So let's say that we have this formula. So after applying the translation, we get this, so nothing special. But then we say, okay, we just collect all the ground terms. So it'll be y, z, and here we also need to introduce, I think we need to use w, where is it? Oh no, w is here, yeah. So we have this y, z, and w, and we just instantiate over the two clauses, get this larger formula, and then from this larger formula, we can just rewrite it into a simpler form, and then what we'll get is that to say that, okay, the set Et is the universe, and then we have this part over the, so W is in the universe, which is in S, so this clause, so this has to be true, and then now we'll need a combination with the reachability part, which we'll see on the next slide, which says, okay, if you can, from W, you can reach Y, and from Y, you can reach Z, well, by transitivity of following the path, you'll be able to reach Z from Y, and that's something you should not do. So here we'll get the contradiction. So, okay, so we see how to get rid of the sets, but now how to get rid of the this reachability part. So actually it's the same idea. So it's again this theory of graph reachability is a local theory. But here now we'll apply the same thing, but instead of having just this few definition of set membership to expand, here we have a whole set of axioms to expand. We'll not go into details, but if you want the details, you can check into this Popol paper by Thomas and Nishant. But what's the intuition between this axiomatization? So that's what I was explaining before, is that if we look at a concrete heap, basically, and a total interpretation, then we have nodes and pointers and everything. But obviously, this might be of arbitrary size, so we cannot reason about the whole heap. So what we'll do is replace those paths by this reachability predicate. So here, basically, we go from a total interpretation of the heap to a partial interpretation. And we can prove that this partial interpretation actually embeds in the total heap if and only if there exists an interpretation of the total heap that satisfies the formula. So that's the part. So that's what is shown about those axioms, that they preserve. So this embedding between the partial interpretation and the total interpretation is preserve satisfiability. And yeah, so that's the key part. And also then for decision that we have all these axioms. They are also proved to be local. So again, we just go to a formula, collect all ground terms of type nodes, instantiate all the axioms, and get a set of constraints which is equisatisfiable. Okay, so that was the first part. So I've seen how we can reduce this separation logic of a singly linked list to this graph reachability and stratified set. And since we have negation, we can, so on top of satisfiability, we can also do the entailment check, because well, we have negation. So that was one of the motivations, so that we have uniform way of dealing with them. But now there is also this question of frame inference and abduction. Or abduction is also sometimes anti-frame inference, so that if you have a formula F interpreted and formula A and B, so you have formula A and B, and you need some time to find the frame. So you have the precondition of a method, you have the current state, and you need to find, so B will give you what will be touched by the method you are calling, but you need to figure out what is the part of the heap which is not going to be modified. And then there can be also the reverse problem of finding the part here that you might need to add to the precondition to the current state of the heap to satisfy B. So for that, we'll need the inverse translation from GRASS to SLL. And what we'll need is just, for the sake of simplicity, currently we just assume that the formula that we have in GRASS correspond to a formula obtained by this translation. We can lift it to any general formula in GRASS, but for just to make it simpler now, I just assume that it's come from translation. And then we'll need a model generating solver, for instance, Z3. So the step is that we'll get those partial interpretation from the solver. So we push the formula F to the solver, get partial translation, partial interpretation, and then from this partial interpretation, we'll just lift a formula in separation logic, then push the partial interpretation as blocking close to the solver and go to the next partial interpretation and basically iterate until we get until the formula is not satisfiable, and then we have the complete frame. So we'll, so actually this translation is mostly of theoretical interest, and we'll see later that, well, we can actually avoid that part when we do analysis of program. So we don't need to go back from first order to separation logic to deal with the frame. Okay, and yeah, how do we lift partial interpretation from to separation logic? So for from the partial interpretation, we'll extract this successor function, which is a mix of the reachability predicate and the successor, like as a function h. which will be the next successor. So if the function h is defined on that node, then it will be the application of h, and if h is not defined, because as we see, we might have just the reachability predicate and not the concrete value. So in that case, we just take the first node that satisfies the reachability predicate as successor. Then we also extract the part about what's called the pure part, so the part about equality and disequality of variables, and just lift everything. So nothing really special. So for instance, what's the use case? So assume that we have a list segment, and then we are in a branch that was testing that x is not equal to z, and then we are just calling that we want to free the head of the list. And the precondition will say that, okay, x has to x point to y, so basically x is allocated. So when it's translated, we get the constraints coming from the if branch, and the rest comes from the assumption. So we push that, and we get two partial interpretations. It says, okay, that x point to z and z might be equal to y. So x point to y and y might be equal to z. And here, the set z will be, in the constraints, is defined as the difference of the footprint of the precondition, so the frame. And also, there might be x point to y and might be a list segment going from y to z. So the list here might be either of length 1 or more than 1. Okay, then we can just leave the translation. So when in the case of so we have the pure part, so the equality and disequality of variables. And then here when we lift, the list is empty, so just is equal to y. And here this part can be lifted to list. And the whole translation says that, okay, we have a list from y to z. And x is not neither y nor z. But yeah. So this part is mostly of theoretical interest, and actually we'll see later how to bypass this. Now the question about one of the motivation was, we want to combine with other theories. So we have proven that this combination actually is stably infinite with respect to the sort node. So we can then use directly Nelson open with theory that have disjoint function symbols. But then what of the also an extension that here we have just one function symbols, but we also lift this using array to many different function symbols. So many successor to represent structures when you have multiple pointer, and you can also do read and write over this field. Now this h, so that when there are many of them, and actually we can combine that with the array theory, so that when you modify one field, the other fields are not changed. Then what when we want to do something more interesting is that we want to combine this translation in a way that is not like purely disjoint as in the Nelson open part, but we also want to express invariant above, for instance, data constraints in the list. So here we have this part which, so here basically the theory do not become not really disjoint, but then become interleaved. So we cannot do that in the general case, but we can do that only if the constraints over the data is again some kind of local theory. So the intuition being local is that say that you can define your theory with a finite set of axioms, and just prove that if you instantiate your axioms over the node that you currently the ground term that you currently have in your formula, that's sufficient. And for instance, we can express sorted list. So there is the first part which is the exact translation of list, but then we have this additional clause that says So here it says that for two variables into y, so y being the footprint of the list, if z can reach y, then the data of z is less than of the data of y. So here we can again use the definition of y into the part, and we get this universally quantified clause, which is local. So here we can have this kind of theory combination. So we can have sorted list and more complex data structures. Then there was the question of trees. So for the moment, we don't have implemented decision procedure for tree. If you have decision procedure for tree, you can do it. But for instance, we can do doubly linked list, because doubly linked list actually is a normal list over which you add additional structural constraints that just make sure that the previous pointer is what you expect. Okay. Now the implementation. So yeah. So basically, the idea is that you start with a program with this separation logic specification and apply some reduction step and get a program that looks like input to boogie, so first order specification. Okay, so here we'll see then examples for how it works for the on this concat example. But the idea is basically you first replace part of the control flow with simpler structures like, for instance, choose and assume. Then for uniformity, we replace loop by tail recursive methods so that we only need to deal with recursion. Then come the instinct part, which is the translation, and also we'll need to modify the formula to add ghost variables corresponding to the heap. So that would be something we'll see with an example. So that then we can also deal with memory access, checking that memory access are safe, and do the frame inference. Well, and then the last part is just okay. So let's look at this example. Okay, do we have a mouse? There's no like, yeah, I don't have the right line separator, so hopefully this knows about. Oh yeah. So basically, the idea is that we start with this program. So first we define the structures. Also, what we want to work is automatically translate that kind of inductive definition into this first order logic. For the moment in the tool, this part, so the translation is hard coded, but we're working on making that automatic. Here, okay, so this stands for the separating conjunction. And then we have this procedure, that's the one I showed before. So that's the input. So now, what does it look after the first step? Okay, so the definition part did not change. Now we just replace the ifs by a non-deterministic statement that assume the condition or assume the negation of the condition. New variables are introduced by avoc statement, so as we would expect, and now we still have loop. And the update to the field are replaced by some update like over the array theory, like we consider next as an somehow as the field is encoded behaves similarly as an array.
You said that you introduce new variables with a avoc statement that looks like.
Okay, yeah, no, they are already declared, but the first time they are used, which correspond to the integer. Here that correspond to this statement. Here we put cure in the scope, but we don't know the value, so that's the avoc statement.
I have a question about that. In your predicate L set, it looks like you have a between the you say x equals y or x not equal to y separating conjunction, but then you have an x in there.
Oh yeah, the idea is to because here we have also so usually you would say that x point to z and this segment zy. So here we just consider this as a memory cell allocated, but without introducing the z, because otherwise we need to introduce a quantifier.
I see. So it's what the separation logic would write as x and then arrow and then like underscore.
Underscore, yeah. But we want to avoid this introducing this existential successor, and here we call this segment. So here we start already in the definition.
Just like the act predicate in Chalice.
Yeah, exactly. So now it will start become interesting. Okay. So here now we start rewriting the program that say, okay, the data structures, the next is just a field pointing to location. And then this segment is into two parts. One part is the structural constraints, and the other part is the footprint. Okay, so and then then we again start to expand the precondition, which then becomes just basically call to this. So it's introducing now here these existentially quantified sets that are the footprint, and it's just basically forcing the constraint that we have. So the union, for instance, that this one is the union of the two, and then we have the leaf, so the domain of this segment. And then the structural constraints that the intersection of the two is empty. So I mean, what you would expect for this part. Then we do this the same for. So here we are in. Yeah. So here we have then it starts to be really big. And then another part that was changed is that also now before we had that loop inside the concat. So the concat actually, the loop is lifted into this whole method, which has pre and post condition corresponding to the loop invariant. And then if we, and then the loop that was in the program before correspond to a call to the method. But also a more dramatic change is that now you see that there are these ghost variable of type, which is called alloc of type set, which are passed into as argument of the methods, and also there are also some other sets which are returned. So the idea is that we don't assume that the prover that we're reducing to has any kind of knowledge about the heap. So basically, we'll just also to do the frame inference and everything, add as ghost variable the part of the heap over which the method is supposed to operate. And then we put some constraints about how to update the heap. So here we'll have this call, that's the return parameters, and here alloc basically was the method which was correspond to the argument that you received when the method was called. So it's carried on over, and then we have the update of after the call, which is that here that's for the moment those two arguments are equal, and so basically we say that the final part of the heap is the original heap. You just remove what was passed as the frame, which is returned here, and then you add the new part which is here. So the method return, for the moment in that translation, the method return the footprint over that was at the call, so that was why equaling, and the footprint after. So basically, it's the difference between the two contain the modification. And then whatever was not in that part, so in the part that was passed, is not changed, will be part of the frame. And we need one more part, because this is just updating the footprint, but it doesn't tell you anything about these function pointers. And here we have this magic predicate that I will explain. So we want to say basically that, so that's the whole heap, or the heap of the caller, the part of the heap that you are modifying. And then we want to say some equality about those pointers, because if they were updated, then the method will know the update, but if they were not updated, they should be preserved. So that will be the frame predicate. And here now we can maybe explain how we did the frame. So the frame, yeah. So the frame now is still work in progress, but the idea is that we want to reduce this, avoid this frame inference. Before I showed you that we can actually reconstruct this frame using this inverse translation. Well, in practice, it does not work because there is this exponential blow-up, mostly of case splitting between equality and inequality of these variables. So what we try to do is just have an axiomatization of what the frame rule, and then prove that we can get some completeness result of this axiomatization and also some decidability. Okay. So what we want the frame to say that any path along this successor edge which does not grow to the frame is unchanged. But for that, what we'll need is to add what we call this entry point. So the entry point of following one successor function in the set big X from X, basically the first node when you follow the H from X is the first node entering big X, and otherwise it's X itself if you don't enter. And then, okay, what the frame is doing now. Let's say for any node which is part of the caller but not of the part that the call is modifying, well, the successor function does not change. So the prime version is the same for all variables. Then we need to reason to say the same about the path. So we say that for any of nodes from any node which is in the frame, and okay, then there are two cases. One will be that say that in the case that there is no path from you to the big X, so EP will be the same because there is no entry point of X. Then anything that you know about reachability is not modified because you can never go in this. You're always in the frame, so you can never go in the modified part. So reachability is preserved. And then the more complicated part is that say that there is a path from X to Y, and you never see the entry point. So basically, it's a path that never goes to to the part which is modified. And again here, the reachability information are preserved. Well, now the question is, we have these entry points. Where are they coming from, and how much of them we need? Okay. Well, we can, again, the idea is, try to use this very powerful tool of local theory. But here it's not a local theory anymore, because if you just take the axiom that we had before and just instantiate over ground term, it does not work. Because in the partial interpretation that you have, you might not have, you have only this repeated path, but you don't have the node which is just at the border between the two regions of the heap. So here we have what we call psi-local theory, that you say you collect ground term, apply some function over that, will generate new terms. And then over this whole set of terms, which will be the ground term that you already have, plus just simply adding EP to those, you can just apply the axioms and get completeness. And here, what's the definition of this entry point? I say that, basically for any x to, the x can reach the entry point. It's just following h or the node itself. Here that says that, okay, if the entry point is of small x is in the part modified, then, then basically this function is idempotent. So if you apply the entry point to the entry point, it's the same node. And then just reachability question that says that, what is the one thing? Oh yeah, that you, for any y which is in the set of in the footprint of the callee, if you follow x to the entry point of x, you'll never see. So you never see further than the first node in the callee footprint. And because actually because this entry point is that idempotent, we can prove that. We're still working on it to make maybe to make the formalization a bit nicer, but the idea is that you can prove that, again, you have this psi-local theory, so you can just take the ground term at the entry point, instantiate the axioms, and get completeness result. Yeah, so the idea is just say that, so if a node X cannot reach the footprint of the callee, then the entry point is the node itself. If you can reach the callee of the footprint, it's the first node inside. And in the partial interpretation that we had before, this node might not exist, so that's why we need this step to introduce the node. And then if you are already inside the callee footprint, then the entry point is the node itself. Okay, so some experimental result that we are dealing with. So just basic list examples. So concatenation, copy, filter, free, and in different versions, single linked list for double linked list, and then the single list, the basic case is just loop, and then we have a recursive case, so we can compare, this automatic translation of loop to recursive function, how much additional work, or actually in general it's even better in terms of verification query that you have to do than the manual encoding. And then we have some benchmark also over sorted list. Then merging sorting algorithm. So this one requires reasoning about the data. But here, well, the data are interpreted over integers. And then we can do also some slightly more involved reasoning that you want to take one list which is sorted, just double the element, prove that it's still sorted. Take two sorted lists of the same length, do sum over all the elements, get a third list, and prove that the third list is still sorted. And yeah. So in general, in most of this, this more complex example, in general, most of the time of the solver is actually spent dealing with the frame. So yeah, that's part of the future work, how to deal better with the frame. But maybe short quickly before the future work. This related work. So this separation logic fragment was introduced by Josh Perdine and his collaborator in 2004. At that point, they had a decision procedure that was basically a set of proof rules, so which was proved to be complete. The idea was either you consider the case where the list is empty, or you unfold twice, so list of lengths 2. And if you can derive contradiction within these two cases, then you are good. And then Byron Cook and his collaborator came with a decidable algorithm. So came with a polynomial time algorithm, which is based on graph and comparing and graph embedding for the entailment check. Then this the translation of separation logic to first order logic is also already existing. So people have been looking at cases which are decidable but without inductive predicate, because you need this additional first order theory which is decidable and match the predicate you want to reason about. Or people have gone to very general translation, but then they don't care about decidability. So we can just embed the semantic of separation logic into first order. Okay, then there is also an alternative with to separation logic when you want to reason about frames. So, implicit dynamic frames, region logic. But I guess people here are very familiar with those works. And also, yeah, people are trying to study the connection between separation logic, these frame rules, and how this into this other logics. What's the equivalence? Then for the reduction to this theory of graph and stratified set, there's also some previous work from first order theory of reachability, how to decide efficiently those in this logic. Yep.
There's also work of Roman Minevich and other students of Rizca heaps. They studied lists pretty extensively in the context of shape analysis.
Student?
Roman Minevich. I can give you some references.
Yes.
They also
there is also.
They looked at leveraging both TVLA with its support for canonical abstraction as well as SMT to decide predicates over the lists.
So there is also a group in Bujanese group that use separation logic, but in general, and also combination with some other theory at some point. But in general, they are looking more like invariant generation, so they don't really care about completeness.
Yeah, that's right. I mean, that's the same thing with shape analysis.
So I think here, maybe the critical difference is that we wanted to preserve decidability, and that's why we had all this complication with this negation and these set theories and avoiding the universal. Yeah. Oh yeah, and then, so we want more examples using this combination of theories, more complex data structures. Okay, and I told you that this dealing with the frame for the moment is still very preliminary. So it works. I mean, so in theory you can prove it that it works, but in practice this tends to be very extremely expensive query to the solver. So we want to try some simpler scheme. The problem right now is that somehow when we go to the translation, we directly expand the predicate with a definition, which is much larger, and introduce disjunctions, so case split. So but sometimes, for instance, in the case of the merge sort, you can actually do the frame inference just by syntactic matching because the predicates are too close. But when you expand everything, it's just become huge formula, and the solver spends seconds solving those. So we want to try some hybrid scheme where you first try not to expand the formula, and well, can you find a frame without expanding the formula? That's related to some work by Matthew Parkinson on separation logic and abstraction. So can we leverage on that? Then the question of trees, sorted, because there are many examples of sorted trees, binary trees, and also maybe how can be taught with lists. And we're also looking at modularity, because there's already some work. We'll see how it ports to our framework, that you have these generic data types, and how do you deal with those generic data types? Because, Thank you for your attention.
More questions?
Sure. Some performance numbers there. How do they compare to doing the same programs in Chalice?
That's a very good question, because at that point when we did this performance number, basically the translation step that I showed you were not done explicitly, but everything was encoded and done in the tool. So we did not have those intermediate steps, so we could not really dump something and try to Chalice. Now we have these intermediate steps, so we can actually try them. Actually, the goal right now would be to say that now we have this, instead of having both the translation and the solving part in our tool, we want to first have the translation, send encoding, then print something that Boogie can understand, and then this decision procedure over graph reachability, encode this as implement this as a theory plugin to Z3, and see if we can just get rid of that, and then we can have probably also much more meaningful comparison with other tools.
So why is Chalice why not Daphne? Why not compare to Daphne? Why is Chalice a more reasonable
comparison? Well, if you do something like separation logic, that is if you
I see.
That's closer to what Chalice is doing.
Okay.
I mean, that is but I mean, Chalice also does fractional permissions, which your decision procedure here does not deal with, right?
No, that's true.
So the fact that you have something that's decidable in Chalice is not decidable, but
in practice that does not mean anything. I mean, in terms of performance, that's true.
Right, that's what I was going to add. Do you think that there are programs that you would be able to do that Chalice wouldn't? Just because you're decidable? Or, Chalice also translates to SMT, right? So, directly, not going through separation logic.
I guess if you program as a bug, my guess is that the solver will be able to give you a model and say that's the bug. Now, I don't know if you have found some case in Chalice that at some point the solver just time out or diverge.
I guess a high-level question you're really asking is that why should we focus on decidability, given that when we try to solve real problems, there'll always be some crap outside this decidable realm. What is the practical advantage that we get by focusing on decidable cores?
Right. Right. That would be a big question. Another big question is, the fact that you're starting with separation logic means that you have to deal with things like the existential that you get when you get the star, that you have to figure out how to split the heap essentially into all these framing and anti-frame abduction things. Whereas in Chalice, you don't have to at all. I mean, it just computes those things. I mean, just like weakest precondition computes things, and for logic, I mean, you need the intermediate steps between, I mean, when you do sequential composition. So I guess the different question is, you're choosing to start with separation logic, which is more complicated, but maybe you could have started with something that's simpler and can accomplish the same things, like Chalice, and maybe you could apply decision procedures there. I don't know.
Okay, so let's say there was one motivation of choosing separation logic was also this question of how we can combine with other theories. So how we can get to the outside of this separation logic world and combine with other proverbs. There was this slide about how we combine, for instance, within the nested open fragment. How do we also combine with, for instance, here we have this question of how do we combine with, not in the nested open fragment anymore, because when you have constraints within that are interacting between the reachability. And well, I mean, that was a question that came to our mind by looking at separation logic formula. So if you change from another framework, those questions disappear, and one part of the motivation of this work kind of disappear. So that was the example we were looking at. Well, then the question of decidability. So that's a very good question, because in practice, this incomplete method might give you better results. But I think there is also this paper from the group of Bart, an eCoop 2009 paper that also do some kind of reduction where they don't care about completeness. And then at the end of the paper, you have one big part of the paper is that, well, if we just do this encoding and send it to Z3, it does not work. And then they do some very complex optimization of the axioms of triggers to make it work. So here, maybe one of the reasons of trying to go for a complete fragment is that, well, if you really want performance, you will need to go down to this business of rearranging axioms, putting triggers, and making sure that it's fast. But here, basically, even in the case where it's not fast, we know that it will not diverge. It will at some point return an answer. So we can somehow bypass this kind of messing around step by trying to have more kind of clear framework. So I don't know how much time because we tried at some point to have just, have this axiomatization and just sending to Z3 without doing this local step and see how Z3 was dealing with them. And in some example, most of the examples for which it's working, it's faster. But for some examples, we just diverge if you just send the axiomatization. So that was the motivation of this more work about decidability, proving it's complete, and so that you can maybe deal in a way that is not more performant with the axioms, but that will at some point give you an answer. So we had this problem of divergence that we encountered. And did I cover all the questions? Or?
Does the fact that the theory is local, maybe another way to say it is it seems like that should help you write axioms in Z3 so that it expands them maybe lazily, but you know that under some amount of expanding,
we tried, but well, not quite. So the problem is that if you look at the axiom and you just apply the axiom, it generates new terms. But the local theory tells you that you don't need to apply the axiom over these new terms. And we have not found a way of Z3 encoding that. I think there is some related work to this local theory actually that was printed at PLDI by Madhusudan and his group, what they call natural proofs. That's just also try to somehow just apply the axioms once and see if you can find a proof. But again, also the difference is that they again are not looking for completeness, but let's say, just try to expand, apply the axiom a few times, and if you find a proof, it's a proof. Otherwise, well, bad luck. Here, by putting that into this local framework, we know exactly when we need to instantiate the axioms and when to stop.
I have a conjecture about that question. So the reason things get undecidable is because of quantifiers in the SMT context. The only, I think people have tried to investigate decidable fragments that can handle quantifiers, but these fragments are not robust. They're very finicky, and it's very easy to slide out of them. The only robust thing that I'm aware of that can handle quantifiers is basically instantiation. And e-matching is the thing that was implemented in Simplify is a particular thing that. So my feeling is that as long as we are stuck with e-matching and there is no breakthrough, like model theoretic breakthrough in handling quantifiers, we are going to focusing on decidable fragments and so on is not going to help us. Because what happens is that you hide things inside theories, but there's a little bit of stuff outside in quantifiers, and that stuff is not visible to the instantiation there, and then you get incompleteness or all sorts of problems. So I think we need some breakthrough in how to handle quantifiers before all this focusing on decidability, all these arguments which are basically essentially model theoretic arguments, they help in doing proofs.
Well, I would rather maybe say the other way around, is that if you have some real breakthrough in the way of handling quantifier, you might just don't need this anymore. But this is some kind of thing
but
that
I don't think that these kind of breakthroughs just happen. They depend on these kinds of things, these kinds of breakthroughs.
In that sense, yes.
Yeah. Okay.
Thank you.
Thanks for speaking.